Um, all right, it's my pleasure to introduce our first speaker of the day. Ethan Woodyard earned his bachelor's degree in wildlife, fisheries, and aquaculture at Mississippi State University in the spring of 2019. During his undergraduate studies, Ethan worked in the parasitology lab of the late Dr. Linda Pote and now Dr. Tom Rosser, where he gained extensive research experience with projects focusing on parasites of wildlife and catfish. Ethan is presently a third-year graduate student working under the direction of Dr. Matt Griffin at Mississippi State University's College of Veterinary Medicine and the Thad Cochran National Warm Water Aquaculture Center, where his research is focused on myxozoan parasites affecting catfish aquaculture in the southeastern United States. Take it away, Ethan.
All right. Thanks for the introduction, and thanks to all y'all for showing up to see this talk. Before I get started on the life cycles I want to talk about, I just want to acknowledge my co-authors. Working out myxozoan life cycles is a pretty labor-intensive thing to try to do, and it's really all hands on deck kind of situation to get some work like this done. So I'm grateful to all my co-authors for getting me access to infected fish and helping out with just all of this work. I also want to thank the catfish farmers in Mississippi for giving me access to their ponds, the Mississippi State University College of Veterinary Medicine vet camp students who actually helped out with some of the necropsies, as well as my funding sources, the USDA and the Department of PPM here at CVM. So my background, like y'all heard, is more wildlife parasitology, but with my PhD work, I've kind of gotten into a little bit more applied work than, what kind of worms live in roadkill. I'm doing more of the catfish aquaculture stuff now, and that's because catfish aquaculture is a pretty big industry, especially in the southeastern U.S. It accounts for over half of the food fish aquaculture in the U.S., and this number changes from year to year, but it's about 380 million in sales annually. Like any aquaculture industry, there's a lot of, well, no, I shouldn't say a lot. There's infectious disease issues, and a big one of these is proliferative gill disease. And you can just kind of see briefly what that looks like here. These are some gills on a wet mount affected by PGD, and you can kind of see with these arrows are indicating some breaks in the cartilage, and that's just this parasite is breaking down the structure of the gills. It's going to cause the fish to asphyxiate. It's a pretty big problem for the catfish industry. Okay. And that's caused by the myxozoan Parahenigae ictaluri. And the way that usually works is you've got this benthic oligochaete living in the sediment of the ponds. These are ubiquitous. They're in pretty much every pond down here. They release this actinospore stage of the parasite, and that's infectious to fish. And now what normally happens in a natural setting is the fish becomes infected. The spores can develop and assist and mature into myxospores. They can be released back into the environment and ingested by the oligochaetes, who then become infected and can continue the life cycle of the parasite. Of course, that's not really what happens in a PGD outbreak. The fish in a PGD outbreak are getting exposed to so many actinospores so quickly that they just can't cope, and there's this massive die-off like you see pictured here on the right. Now, if we want to study this in the lab, we don't really have a great challenge model to fully maintain this life cycle in the lab. What we have to do is rely on outbreaks like this. We'll go to a pond where they're having a PGD outbreak with a big fish die-off like you see here on the top left. We'll wade through the rotten fish carcasses, get out in the pond and collect some mud to try to get these oligochaetes that are infected. We'll bring the mud back to the lab, clean it up, and we'll plate these worms with transfer pipettes into individual wells in 96 well plates. And you'll see on the right, this is from a recent collection trip. And you'll notice this is about 5,000 worms. And the reason we have to do so many is because prevalence, even in a PGD outbreak like this, where you have a trailer full of dead fish that's just wiped this pond out, prevalence will still only be, maybe 2 to 4%. And you need a good 20 or 30 infected worms shedding actinospores to really do fish challenge work. So that's why we have to plate so many. Obviously, a better solution would be if we could get a laboratory source of these infected worms. Of course, that's been tried. This sort of tower over here on the left is something that's been adapted from research that's been done with other myxozoans that are problematic for fish. And the way that this was meant to work is that here in this tank on the top, you would have infected fish, and they would release their myxospores down into these tubs that would have cultures of the oligochaetes, Diro digitata, and we would just kind of monitor those to try to see if they eventually became infected and shed actinospores. Unfortunately, that never worked out. We've later found out that the way that these were set up for the Diro, there's a lot of water movement, there's a lot of agitation from the aeration. It turns out they don't handle that so well. But in either case, this kind of never really panned out like we had hoped it would. Another approach might be to take infected fish directly and kind of isolate these cysts that have the myxospores in them, isolate the myxospores from those cysts, and then put those directly on these kind of stagnant tubs of Diro that we found to be a better way to culture them. And the way that we were culturing those Diro was with this method that we thought worked pretty well. The Diro would split so much, they would asexually divide and reproduce to the extent that about every 2 weeks, you'd have to split the culture off because otherwise the population density would just get too high and the culture would crash. But every time, pretty much every myxozoan student that's come to the lab has tried to infect these worms before, and they would die every single time we tried to infect them. We've tried it with Aegyptoluri, we've tried it with a few other Hennegai species from catfish, and it just never seemed to quite pan out. I tried it when it was one of the first things I tried as an undergraduate student in the lab, and my worms also all died. But while I was an undergrad in the lab, part of my responsibilities was to look after these cultures of worms and also tend to our cultures of aquatic freshwater snails that we use for some of our trematode challenge work. And the way that we had this set up was with the snail tanks next to the Diro tanks. And on the recommendation of a colleague of ours at CVM that also grows freshwater snails for some of their aquaculture research, we started supplementing the snail's diet with this commercial algae wafer. It's a commercial diet that's made for feeding like Plecostomus and other like algae feeding fish like that. And one day I just decided to throw some of the wafers in with the Diro because they were right next to the snails, and I just wanted to see what would happen. And what happened was this paper here. It turns out that was actually a really good diet supplement for the Diro. You can see these Diro on the right look a lot more like what we would expect to find in the catfish ponds. They're just more robust. They're splitting more often. So I figured these Diro seem to be doing a lot better with this new diet. Maybe we could try redoing those challenges and maybe we'd have better success. So these gills are actually infected heavily with Hennegai exilis. This is from a diagnostic case that came to the lab at MSU CVM. Actually, the day that we shut down for COVID, this came in. And I went ahead and set up challenges, got special permission to keep coming in the lab, even though we were shut down. I was glad I didn't have to take the Diro cultures home with me. But I set up cultures like we had before, except for with Diro fed with the new algae wafers. And also just for fun, I fished this cup out of the garbage, set up a Diro culture in it, and just threw an infected gill tissue in there. I didn't prepare it in any way. I didn't isolate the myxospores. I just threw it in there just to see if the laziest possible way of doing this would end up working out. And so I kept the Diro cultures going, just let them sit for a month to kind of just let the myxospores sit with the Diro and hopefully they would ingest them. And then starting at 4 weeks post-exposure, I played all the worms. I check them on a inverted scope like this. This was my COVID summer here. It was mostly just checking these worms every week until we observed shedding. And sure enough, it actually worked out. You can kind of see here, there were some actinospores released. And that actually worked out for Hennegai Aegyptoluri. We got from morphological and molecular data from both these myxospores from the fish and actinospores released by the worm. They matched up. So we've got that life cycle going in the lab. It worked for Hennegai exilis. Same thing, morphological and molecular data from myxospores and actinospores matching up. And Hennegai mississippiensis. And these are all just from diagnostic cases that were brought to the lab. And we even got a novel species of Hennegai. We hadn't seen this myxospore or actinospore before, but now we have a novel species, myxospore and actinospore, Those of you that in the audience that work with mixed zones know this is kind of like a rare thing to get to do. I feel very lucky to get to describe a novel species, which is common to do, but to describe the whole life cycle of it as well is it's a privilege to get to do that. And we're probably going to name it after the late Linda Pote. She's just contributed a lot to our understanding of the biology and life cycle of hennig eyes and catfish. So it seems appropriate to kind of name this thing after her. So in addition to all that, that's kind of part of my dissertation work. We also do this every year. We do a MSU CVM summer vet camp. This is for kids aged 10 to 17 that are aspiring veterinary students, or they want to work in allied fields. They can come and attend a series of workshops to just kind of get exposed to what they're signing themselves up for if they choose to pursue this kind of career. And one of those is, of course, an aquatic parasitology workshop. So those happen in the afternoon. And what we would do is every morning that those were going to happen, we would go out to a local creek and collect fish, just because we wanted to be able to show the students live parasites. When I first started learning parasitology, none of it really meant anything to me. It's just dead things on slides. But when you see a live parasite, it really makes much more of an impact. And I just hope that we're able to do that for these students. So we would collect these fish, take a subsample of them, and just do a full parasitology workup on them with just myself, Graham, and his students to make sure we're not setting these students up for failure. We don't want to give them a bunch of fish that have nothing in it and get them all excited about finding parasites, and then they don't get anything. But we would cut up a subsample, and we actually ended up finding a novel Mixobolus in the gills. Two novel Mixobolus species in the gills, actually. And we know that they're novel, they're distinct from each other and from previously described species from closely related fish hosts. And I know that y'all can't see this table, but just to show we did our due diligence, we actually, did a fairly exhaustive morphological comparison, and they're distinct from each other and distinct from previously described species. Now, this part, I did a little bit of experimental work here too. I find often when I see people present their experimental methods, I can get a little lost. It gets kind of complicated. They've been doing this for months, and to them it makes sense, but to me in the audience, it's not necessarily as clear. So I hope that doesn't happen here. What we did with these fish after the students got done with them is we took their gills and we put them on tubs of worms. And we just did that for all of them. I can't see anybody's camera, so I'm just going to assume that went over very well and I'm hilarious. But anyway, we just throw the gills on there and then plate the worms as before to hopefully maybe get the actinospore stage of these novel Mixobolus species. And sure enough, at 5 weeks post-exposure, we actually saw some actinospores. So I had 68 of about 150 of the exposed Diro were shedding. So I took a subsample of actinospores from each individual Diro that was shedding and sequenced a little bit of the 18S ribosomal RNA gene to kind of identify them molecularly. And it turns out it's actually the actinospores of both of the novel Mixobolus species. So we actually have the two novel Mixobolus species and their life cycles just from these gills that we threw on a tub just to see if it would work. And that is supported by our molecular data. And the molecular data includes both 18S and 28S ribosomal data, as well as this elongation factor 2 data from actinospores and mixospores of both species. And I want to just kind of point out briefly that there's not really clear cutoffs for what separates species, like what degree of similarity constitutes a novel species. This would probably they're morphologically distinct, so I feel like we could get away with this, but I don't feel super comfortable with percent similarity in the high 90s being used to justify separate species. But having this EF2 data, I feel a lot more confident saying that something that's 86% similar is a different species than I do saying something that's 96 or 98% similar is a different species. But anyway, the identity of these two separate species and their mixospores and actinospores is supported by our concatenated phylogenetic analysis using all three regions. And this is just Bayesian phylogenetic tree we made in Mr. Bayes. And you can see these dots indicating 100% nodal support for this actinospore from Diro 67 matching Mixobola species 1, and this actinospore from Diro 12 matching species 2. And I also just want to point out kind of briefly that there seems to be some, in the phylogenetic analysis, the myxozoan species seem to be clustering by worm host, which is kind of interesting. I'll kind of follow that up later when I talk about my future directions. But just to kind of have a recap of what we've got so far. We've got these 3 Hennegaia species life cycles. These were known from worms and fish sampled from catfish ponds previously, but we've now replicated those life cycles in the lab. We've also got a totally novel Hennegaia species with its life cycle replicated in the lab. And then 2 novel Mixobola species from these Pimephales notatus that also use Diro digitata as a definitive host replicated in the lab. Where I want to take this work in the future is, like I talked about with that clustering by myxozoan species by the worm host. I kind of want to look at some of these and see if maybe we can expose Diro to these and maybe elucidate their life cycles, because these are not known. And the other people have looked at this. I doubt that it's this simple that all these just happen to use this same worm host. But if I were going to pick a worm to try to experimentally infect with one of these, I would probably pick Diro. So now whenever I get fresh myxospores, I just go ahead and throw a subsample of them onto Diro and just hope that it works out. And the other thing that I want to kind of do with this is, you can see we have some preliminary data here of how long these worms shed their actinospores for. And we've already got some kind of non-overlapping timelines for when they're shed. And this might be a previously underappreciated force that's driving myxozoan community diversity in the catfish ponds. But you'll notice they all kind of end at 84 days post-exposure. That's not because they actually stopped shedding, that's just when the experiment stopped, because like I mentioned before, for the first 4 weeks of these challenges, I don't look at the worms. But then every week following that for 2 months, I look at them, and these populations of worms are doubling. I'm plating them individually in 96 well plates. So that's, that's about a 10-hour day to plate all those, and then another 10-hour day the following day to look at all of them. So after 2 months of that, I don't know if the worms were done, but I was. So we really should follow this up and kind of take it out for longer for each individual species to see how long they shed for. Yeah, and I think that's about it. I'm happy to take any questions.
All right, very well done, Ethan. That's very cool stuff. Congrats on finding those new species and doing the hard part with the life cycles. All right, Jim Winston's got a question.
Hey, Ethan, thanks. That was really interesting. These are difficult experiments and difficult systems to work with, as you know better than anyone. It's been done only a few times, so congratulations on getting that to work. One of the things that came out of your work, and I think some of the work of Jerry Bartholomew and others, is that it appears for some of these that the host restriction is in the worm side and not necessarily on the fish side as much, although there certainly are some of them that seem to be more fish specific. But I liked your idea about using the Diros for some of the other myxosporians, and I'm wondering, do you have any evidence that the other worms can host any of these Hennegaias or the other myxosporians that you've worked with?
So we haven't seen any of these in multiple worm hosts, but it's also, there's kind of an issue of biased sampling with these, because we know that H. ictuluri is associated with Diro digitata, so most of our sampling is restricted to that. I have a few times plated like tubifex, and some of the other species that we see in these ponds, and we don't really see any that use multiple worm hosts.
Yeah.
But there's also sort of a problem with that in the literature, and that people don't really go out of their way to identify the worm host as well as they do fish. They just say it's this worm, and then there's not really data. So I think when people are looking at that now, they're finding that some of the worm hosts have been misidentified. So it's all kind of a mess.
Okay. Thank you.
Thank you.
Any other questions out there? All right, Chris.
Hey, Ethan, good talk. Just on your two Mixobolus species there, that 96 some odd %, you're probably fine on that small subunit gene in terms of distinguishing two different species, and you've got the morphology as well. So yeah, that's probably pretty reasonable to make that argument. I had a very similar question to Jim Winton, and I was thinking more from the perspective of that duration of shedding and sort of the suitability of the host. Is there a lot known for mixozoans about that duration of shedding outside of what you've done? Has anybody else looked at that? Could the period being shorter for your experimental exposures with those new species be indicative of this maybe being more of an experimental host versus a natural host? What do you think about that? I'm curious to hear your thoughts.
So as far as being an experimental versus a natural host, I don't think that anybody, at least not with these, has really looked at them for a long period of time. We're usually just trying to get some to throw spores on fish, but it is something worth following up, whether like how long they keep shedding for. Does that kind of get at what you're?
Yeah. So you're saying nobody's really looked at these sort of longer term kinds of duration of shedding. Is that what you're saying?
Right. It's been like a few weeks at most. And I think the big focus with that work that was done in Bellerud's dissertation was with H. ictuluri, and it was about a week that they were shedding.
Yeah, it gets me thinking about some of these digeneans that, in say the snail hosts, where some will shed for a very short amount of time, some are really long, and so there's a lot of variability, and maybe we just don't know all that much with mixozoans. So yeah, it's very, very interesting contribution. Yeah, thanks.
Thanks.
Yeah, I had a question. Oh, great. Yeah, really fascinating talk. And I'm curious, thinking about worm shedding over time, is it the infections, are they going away, or is it just the more uninfected worms are being born?
So that is actually that's kind of a problem with the way that we've done the challenges, is because they're just in this tub. That's kind of a question we don't know is, I replate them every week and then put them back in the tub. But the ones that I see that are shedding one week, is that the same ones from the last week, or, have new ones started shedding and the old ones died? The way that I want to address that is by probably doing these challenges in like 24-well plates where we individually put mixospores on the worms. But with this, this pooled challenge in the tubs, we can't really know a lot of interesting things like that. We can't really sort out from our current challenge model.
I see. No, but fascinating. Congrats on the life cycle. It's opening new fields.
Yeah, thanks. It's I did not expect, like, we've been trying to do these for like 30 years, and then all of a sudden 6 of them work. Like, I did not expect any of this to work out the way it has.
Very cool. Any other questions out there?
I've got a quick one for you, Ethan. I'll echo everybody else. You do a stellar job, stellar work. So hats off. I wonder, I'm thinking more on the Diro itself. Do you know, how about temperature ranges for the worm? Like, is that something that you could potentially use for some of these cold water mixozoans, or that's pretty much like a warm water organism? Like, what do you know about the temperature ranges of the worm and its life cycle?
Man, y'all are just finding all these like critical flaws in the No, it's actually a really good point. The temperature that I kept these worms at is just room temperature as a matter of convenience. But the temperature that we see outbreaks of, like H. ictuluri, for example, in ponds, is actually higher than that. So I'm wondering if we probably need to adjust that to get optimize the shedding rates. As far as the temperature of the range of Diro digitata itself, I'm not sure, to be honest.
Yeah, I guess to clarify, then no, I'm not pointing out any flaws. Mainly, I was just thinking you piqued my interest with suggesting that Diro is a good thing to use if you're trying to figure out a life cycle. And you know, we've got a bunch in the Great Lakes, and it'd be nice for me. I have no idea what a leaky to look at for some of these things, right? So yeah, just thinking more along the lines of that. So, thanks.
Yeah, it
Thank you.
might be a little warmer temperature to speed the process up. You wouldn't have to sit there so long.
Right.
All right, so no questions in the chat, Ethan, but there are some compliments, so be sure to check that out. Virtual round of applause to you. Very well done.
Thanks.